you for taking the time today to join me at the Leeds Digital Festival to talk about something I'm really interested in. I've been dying to have an opportunity to talk to you about. So I'll just tell you who I am. So I'm Tom, and I've worked for Covéa Digital for about 2 years now. And my current role is a data scientist. So I spend most of my time trying to solve problems with fraud, trying to get the most out of our data. And I suppose you could say my passion in that sort of was rooted very much in some of the topics that we're going to be talking about today. So I'm really excited to be able to tell you about what exactly is quantum risk analysis and what it really means for us and for the world as a whole, really. So the first place really to begin is why am I interested in this slightly bizarre world of physics? And really, it starts kind of with this image. This is a very dense photograph, to put simply. What this is, it looks at the top like something you'd see off Google Maps, but then as you drill down, you can see there's lots of very strange layers. Those are layers of electromagnetic radiation, essentially, and other spectral bands. So when you take a picture, normally you have your red, green, and blue, and that makes the image that you can see. Well, not only have we got that, as you can see on the top, but we have many other layers. So we've got infrared, we've got ultraviolet, we've got radio waves, we've got all kinds of signal taken from a very special camera in a satellite. And there's a problem here because we need to know what sort of land is fertile on Earth, which land isn't, and it's quite a difficult challenge. We can't survey every inch of the Earth to see how fertile the land is, but you can use various techniques. So one way is to use what's called a spectral signature. And that works by looking at the combination of these waves. So what the emission is of infrared, the emission is of radiation is of, I don't know, radio waves or something like that. But you can work out what exactly these materials are. So that this cross section of a field or fields you can see on the top, we can identify whether it's fertile soil, if there's any fertilizers there, what crops it might be quite useful to grow. But what really excited me was that this is quite a complicated problem because the dimensionality is quite high. Dimensionality is where, as you can see, you have not just got a small cross section at the top, but as you can see, it goes really deep. In fact, 220 layers worth of data to analyze. And that's quite hard for a normal computer to do. And not just in terms of time, but in terms of accuracy as well. So this led me to look at a technology, but even then in 2017, when I started to look at this, was still pretty in its infancy, was quantum computing. And I want to sort of talk you through a little bit about my journey on how I learned that quantum computing could solve problems like this, and what applications it could have for us as a digital function in an insurance world and wider. To understand kind of quantum computing, it makes a lot of sense to try and understand, well, what are computers themselves? How do the computers that we're using today to talk about this presentation on, to receive, our smartphones, they all have, when you boil it completely down, some very key things in common. All they do is process binary, and that just means ones and zeros. Sophisticated computers can process a lot more binary. Simple computers can probably process less. But the point being is that is the same concept that we have had since the beginning. Now, computers have immensely improved since the early 30s when we were really starting to use them. Now we have more storage than we've ever had portable, in our devices. We have more computing power than we've ever had. And every 2 years, we know there's a law called Moore's law, which predicts that every 2 years, the amount of compute power and storage and so on generally doubles every 2 years, which is quite exciting. So we're on a really strong path of growth, but that won't stay the same forever. Quantum computing works on a fundamentally different scale. Instead of using the physics that we know and understand, gravity, why the fact that I'm still sat on this chair and not floating around a room, and why every time you press down on something you get an equal and opposite reaction, well, computers as we know it follow those rules. They are a student of classical physics. Quantum computers aren't. They rely on completely different ideas. And I'll take you into some of those now. But just to give you another indication of why I was really interested in this, it was Albert Einstein that said, I think it was the one thing that genuinely flummoxed him about physics, and he described one particular part of quantum mechanics, which we'll talk about, as spooky action at distance. And I just think anything that Albert Einstein found immensely complicated is definitely worth researching. So the point here on this slide is that classical computers and quantum computers aren't just different because one's more powerful. They're fundamentally different. Quantum computers operate on the lowest known level of physics, below gravity. The very fabric of our universe is the same rules that define how a quantum computer works and how the universe lives itself. So it's a really exciting and quite strange idea. To understand how they work, it's important that we talk about two elements of quantum mechanics, and we're not going into low-level detail. I don't think we need to, but the point remains that there are two things of many that are really interesting. The first one is called quantum superposition. What you can see on your screen, some of you might be quite familiar with because it's been quite popular in culture, I suppose, as history has gone by. Some of you won't. This is the Schrodinger's cat analogy, but don't worry, no cats were harmed in the making of this presentation. And Schrodinger's cat is meant to illustrate in a rather strange way how quantum superposition works. The basic idea is that Schrodinger, who was a very famous physicist who worked extensively in this, so it makes sense that he would do this, had a cat, and I don't know whether it's true or not, but put it in a box with some kind of poison in there. Now, the key point here is that you close the box. You do not look into it, you don't see it, you don't hear it. You have no idea what is happening inside that box. The cat has two choices. It either consumes the poison and dies, or it doesn't and lives. The point here is that you don't know that until you open the box. So until you observe this quantum system, obviously at a little bit of a bigger scale, you don't know whether the cat's alive or dead. And in fact, until you observe it, it is simultaneously in both states. It is both dead and alive at the same time. Sounds quite impossible, but in fact, this is a real postulate of quantum mechanics. This can happen. To formalize that a little bit, and I want to draw the analogy back to classical computing, because there's one quite common misconception about quantum computing, is that it inherently fights everything, all the computers that we have. Every computer will be replaced by a mega quantum machine. Well, that's not entirely true, because quantum computers work together with classical computers. In other words, every other computer that we have, because one needs the other. We can't understand information that's encoded into a quantum system. It's not possible. So we need some help with a quantum machine, the classical machine. But just to analyze the point, the classical computer, as we said on the slide before, works on having a 0 and a 1, like a switch, a binary, off and on. Well, we also have the same thing with a quantum computer. 0 is 0, which is off, and 1 is on. We have a different notation called Dirac notation to show that now we're not talking about classical computer bits. We're now talking about the qubit. The qubit is the analogous representation of a bit, but in a quantum system. And the interesting thing is, a classical computer, a bit is always either 1 or 0, regardless of whether you think about it or not. Well, if you look at it at a low enough level, then it is technically a quantum system. But with a classical quantum system, the state, as you can see on the bottom, is actually a linear combination of both the amplitude, in other words, the probability of it being 0, and the probability of it being 1 at the same time. So you can imagine when it's in this state, you haven't yet opened the box. You don't know whether the cat is dead or alive. It's only when you open the box that it actually collapses into an actual state. So the probability, the alpha of it being 0 and the probability beta of it being 1, they're going to be slightly different levels. Hence why it always decides what it's going to be. And that's really interesting, because that means once the quantum computation has been completed, we can understand what that information means, because it still is either a 0 or a 1. But the point being, until you observe, it is both at the same time. In fact, it is an almost infinite number of states at the same time. And this is one of the reasons why quantum computing can be so powerful, because you can only model a couple of states with one bit, whereas now you can model almost an infinite number of states. So already, you know, the capacity has gone up hugely. The second and probably the most profound element of quantum mechanics, and I'll explain why you're looking at a very grayscale image in a minute, is called quantum entanglement. And this was the very phenomenon that Albert Einstein described as spooky, because this should be impossible. It shouldn't be able to happen. How? And I'll explain why. Quantum entanglement is when two separate particles, so electrons in this case, while they are completely separate, they are connected in some way by some mysterious force that I certainly don't understand, and I don't even think the greatest academics really understand at the moment. But the state of that system, let's say it was the cat and the box, they are linked. You cannot separate them. The state of one depends on the state of the other, and vice versa. And the most amazing part of this, it doesn't matter if those two atoms were at the other ends of the universe, they would still have a link with each other. So they're not separate. This is the first ever photograph of a confirmed, arranged quantum entanglement. This was captured by the University of Glasgow fairly recently, I think. These are two electrons, and they're actually in a state of strong quantum entanglement. So they are, for the purposes of what you can see in this very small snapshot of time, they are separate, but they are also pretty much the same, and their states depend on one another. How can we use that in quantum computing? Well, amazingly, that allows us to encode pretty much double the information, because if you've got one qubit that's suddenly inextricably related to another qubit, well, all of a sudden you can store even more information. So this allows for principles such as superdense coding and all kinds of, again, that could almost provide exponential speed-ups and exponential storage capability, because we're not using the same rules. We're in a different ballpark now when we talk about quantum. So the two foundations are really important, are entanglement and superposition, and we're going to see how they play a part in making quantum computers very powerful. But it's all very well talking about the physics and the theory and being all excited about universes and quantum mechanics. What use is it actually to us? Specifically, what use is it to quantum risk analysis? Well, over the years, we've discovered techniques to manipulate these little electrons and particles to do what we want within reason. What you're looking at here is a very simple example of a quantum circuit. Now, we have circuits with normal computers. A CPU, in a way, central processing unit, the brain of a computer, is a circuit, a very complicated one, but a circuit. So is this, but based on quite different ideas. So the 5 lines that you can see at the top of the diagram represent 5 qubits. So that's those linear combinations of 0 and 1. Although at the start, they're all 0. They're kind of at rest. And we do this, if you're interested, by cooling them down to an incredibly low temperature. I don't know the exact, but it's in Kelvin, it's that cold. That allows them to be calm and rested before we start throwing them around. But those boxes with the H on them, they take that qubit that's in a restful state and put it purposefully in superposition. I don't know how they do that. That is definitely more of an engineering challenge, which I would never understand. But they can put this little electron into a state of superposition. And that means, as we saw earlier, we have the strange probability of it being a 1 or a 0. And we do that to all 5 of those qubits. And you'll see the cascading little boxes with what looks like a dial in there. They're measurements. This is the crucial link between the classical world and the quantum world, because we take that very strange, entangled, superposed information, and then we open the box. Whenever those grey boxes are listed, the boxes are opened. and we can see what's inside, and therefore we can see the state. And you'll notice that they come down onto a measurement line. And the key point here is that that results in binary that we understand and have understood for years, and computers can process the computers that we know. So we can make quantum computing practical. It's not just about the amazing quantum physics underneath it, but it's also about the engineering. And this is a very simple example. Quantum circuits can be horrendously complicated. Just to show you one of the most amazing, I think, and one of the oldest applications, or at least theoretical applications of a quantum machine, is to do with factorizing prime factors of very large numbers. Now, it doesn't really matter what that is, but what does matter is what is underpinned, or what is underpinned by using this. So every password that you've probably ever used when you're online banking and you're on social media is, if they say it's encrypted, it's probably using something called RSA encryption. And that's based on the idea that it's really, really hard to find the prime factors of big numbers. And when I say really, really hard, talking years and years and years, sometimes tens of thousands of years, sometimes it might take you the length of time the universe has been in existence to crack the password. But it was discovered that this is a type of problem that a quantum computer can do really well. And early on, there was an algorithm developed by Peter Shor, and this algorithm finds a way to factorize prime factorize large numbers with a predicted exponential speedup, which means it is almost infinitely quicker than any classical computer we've ever had. The implication of that is that potentially every password that's ever been set and every secure form of communication could be instantaneously cracked if we had the right quantum computer to do it. That's quite a scary concept, and so much so that there are many organizations set up to deal with the idea that we might be able to crack cryptography, even the most advanced cryptography today. The only way you can fight this is by using quantum itself. So quantum cryptography is a rapidly growing field to try not just combat against quantum cryptography, but to develop inherently secure communications. I just wanted to share that as an example of how there are some real and very profound applications of quantum computing. But what does this all mean for risk analysis? Well, in insurance, one of the core things that we do as actuaries, we are studiers of risk. We understand what risk means. We understand what risk, or we try to understand how much a risk costs to insure. A risk might be the risk of you having a car accident, or the risk of your life, because health insurance and life insurance is based on really how risky it might be for you. And that's the core of our business. We do lots of other things, but really underwriting and trying to understand risk is absolutely central. One of the methods that we use quite a lot, and not just us, lots of places use, is what are called Monte Carlo methods. I'll explain a little bit about what those mean. What you can see in front of you is what's called a normal risk distribution. So let's take the analogy of school exam results. I suppose they've been quite topical recently. At the bottom of the diagram on the left, let's say that they're the really poor students. They're not quite performing as well as they should do. You'd hope there aren't so many of them. So the curve is quite shallow. And then as we move up to the middle of the curve, we've got your average people, your B grades and your C grades, lots of people doing them, that's fine. And then equally, as you get to the top end, you've got your very high performing students, straight A's. It'd be great if everyone was like that, but then I suppose that would defeat the objective of exams. But there's much less of them. So this is a normal distribution. There are many different types of risk distributions. What that means is, so let's say the risk was on the bottom, I don't know, having a car accident or a particular scenario, and then on the axis on the left, that might be the cost associated with that risk occurring, or the probability of having it. So you can see that we can apply these graphs to all kinds of situations, and to compute the potential cost of a risk and the probability of it occurring within reason, Monte Carlo methods are used, and they're based on the idea of chance and randomness, which is why they have the name Monte Carlo, based after the famous casinos in Monaco, or at least so they say. So we use them all the time, and that helps us understand risk, which helps us understand how we can do business. So they're pretty important. There is a problem though. As risks get bigger, as the more things you want to analyze get bigger, or the amount of data you want to process, it gets a bit harder. In fact, depending on the algorithm, which is just a set of instructions to solve a problem, it can get very much harder. So like factorizing those prime numbers, for example, that is almost an exponentially difficult problem. So you might see, let's say the dotted line on the far left, you can see as n increases, so let's say that's input of numbers or size of number. As that number increases, you can see the difficulty, let's arbitrarily say that's on the left, goes up massively. Whereas you might have a very efficient algorithm, let's take the blue line at the bottom, as the problem size grows, it doesn't really get that much bigger. That's quite efficient. But just like with the image that I showed you right at the start, as things get bigger, as the dimensionality grows, it gets a lot harder. And this is a problem. Sometimes they call it the curse of dimensionality. This is a problem with Monte Carlo methods. Now, that doesn't mean that they're completely flawed. Lots of work has been done to try and improve them and tweak them and make them more efficient. But there's only so far you can go using computing that we have today. So a team at IBM, IBM have been around since the dawn of computers, and one of the heavyweight investors in quantum technology decided to have a go with this problem. So they tried it on a small scale, so it wasn't huge, but they did try this on a real quantum computer. What they managed to show is they built an algorithm using, so in other words, a quantum circuit, a very big, complicated one, that was able to accurately price a risk quicker and to a higher accuracy than a standard Monte Carlo method. In fact, they did so well at this, it was over 4 times faster. And the estimation error, in other words, how accurate it was at its risk, was better as the problem grew. As you can see the difference, the quantum algorithm on the bottom side, you can extrapolate that out and you can see the gap gets even bigger between the Monte Carlo method. So we're seeing yet another improvement, 4 times better. To put that into perspective, this means that let's say you have a risk portfolio to process. That might take a couple of weeks on a relatively hefty supercomputer. Bearing in mind the Monte Carlo method tries many combinations of random numbers and variables within the risk curve to try and profile what that risk looks like. That might take weeks. Well, a quantum algorithm would probably be able to do that in real time and on an absolutely massive scale. That's really quite powerful for us because risks change all the time. We've seen the world completely turn on its head. So if we're not able to accurately profile how risks change with health, with motor cars, people driving less, with us going out in different ways or not going out as much, how can we remain dynamic to risks changing? Well, one way is if we were to use quantum computing, for example, we could process risks exponentially quicker, probably, than our competitors or indeed anybody else on Earth. That's very hypothetical. A lot of this is still very much in laboratory situations, but the point remains it's a potentially enormously powerful development. I want to leave you with a few interesting thoughts about quantum. By the way, that image there is actually the IBM quantum computer core that was used to try and calculate these risk profiles. I have no idea how that works, but it looks very beautiful, and they run it at an enormously cold temperature. In fact, that leads me to my first point. Quantum computing is by no means a fully stable, excuse me, and commercially ready technology. I always liken quantum computing to where we were in the 1970s with regular computers. They're very big, they're probably very noisy, they use lots of energy, and well, they're not that great. A quantum computer will not be any better at solving your tax return than your Excel spreadsheet would be. But there is one reason that I believe quantum computing is genuinely going to be one of the biggest revolutions in computing and therefore I'd say modern humanity that's ever existed. Because if you look back, and in fact a famous physicist called Richard Sutton did the same. He looked back at the greatest technological innovations that we've occurred in the machine learning space. One of the most notable ones was in 1997. I think he was called Gary Kasparov, the grand chess master. Well, IBM managed to beat him at chess. This was huge because for the first time, an artificially trained system, without a human telling it what to do, we programmed it, but it learned itself. It searched for solutions and it learned itself, beat a human at a very human game. And then much later, I can't remember, is it 2005 or 2006, Google, with their platform called AlphaGo, managed to beat, again, a grand champion in the even more horrendously complex game called Go. The common themes with these two developments, and countless others besides, is that they relied on two concepts called search and learning. And if we look back to the graph that we discussed earlier on the complexity chart, they're one of the steepest that you can get, because as problems grow, they get so difficult to solve. So difficult that if we wanted to try and find a solution to a complicated problem like that on a normal computer, well, you could be taking 10,000 years. What a quantum computer does is lift the ceiling in terms of computing power, not just by a little bit, but by an enormous amount. So they postulate that we will get better, not by trying to replicate exact processes of how humans might learn, how we assimilate information, but by using search and learning, the two most computationally intensive processes that we could possibly think up. And we reach the limit of what classical computers do. With quantum machines, we could see some of the most progressive problems being solved in history. Quantum risk analysis is one example of a pretty profound reason, and it could be used in a number of different ways. But it's a different paradigm with quantum. It doesn't rely on the same rules that we understand. It works in a very quirky place. And we're still developing it, but I think it's going to be particularly powerful as time goes on. So if you have any questions, feel free.
Thanks for that, Tom. So if anyone does have a question, there's a couple of ways that you can ask. So do feel free to just come off mute and shout out and ask your question, or you can use the chat box. If you want to type your question in there, we'll pick those up. So yeah, any questions, take it away.
It is a bit of a revolutionary thing, so I can understand why you might not have any questions on it. But the main takeaway for me is consider it in the future. I think quantum will be pretty revolutionary, and it's something I certainly want to focus on in the future.
Sorry, I've got a question, Tom. Firstly, I'm sorry, can you hear me?
Mm-hmm.
Good. That was a really good overview. I came in 5 minutes late, but I think I got it. I've seen various things in the trade press about how it's going to take less than 3 years for the Chinese to basically decrypt all encryption using this stuff. But clearly that depends on the speed of the adoption of these phenomenally expensive bits of kit. And obviously you get the odd organisation like IBM who can make it. Have you got any idea as to how quickly this is going to get to the point where we all need to revisit completely our encryption?
I think there's two ways to answer that. I think theoretically, and at least in a laboratory, we're probably there at solving these big sort of problems. But as you kind of summarised, they're very big and they're very expensive, and not everybody has one. I managed to use IBM's because they've sort of made theirs available, well, on a very limited scale, but not to solve encryption problems. But I think the engineering challenge of building quantum computers is much harder than the mathematical and computer science challenge, because those machines to get an atom to be so stable that it's not moving around so you can observe what state it's in, means you've got to cool it down massively. And it also means that it is incredibly susceptible to interference. The universe itself is making an interference around it. So I think, we could see within the next 10 to 15 years some very serious contenders for more practical computing. I don't know if they'll able to solve every password from one location. I think that would have to be a bit more of a team effort, but it is a real possibility. And as I said, you can look it up. There are companies designed, set up, and built to try and combat against these things, because it will happen. And I think we should all think about quantum computing. Well, I'm slightly biased, but it is coming, and it will be huge.